Right. Well, thank you everyone so much for joining another Balerion Space Ventures podcast. Today, I'm joined with Andrew Coors of Steelhead Composites. It's April 17th, and we're going to be talking about composite overwrapped pressure vessels. Something that maybe a lot of people don't know too much about, but it's quite important. Uh, Andrew, thanks for being here. Maybe to kick things off, for people who've never heard of Steelhead, what's the simplest way to understand what you guys do and why it matters?
So we were started in 13 years ago to solve a problem that required using advanced materials to lightweight an industrial component, and that was resulted in us taking a lightweight metallic component and reinforcing it with carbon fiber. So we had a great combination of strength and lightweight, resulting in a 1/10 the weight. And that's pretty critical for anything that goes in the air or in space, having that lightweight, the high strength, and the reliability that we have done for the last 13 years.
Got it. And these pressure vessels, they look like a big CO2 tank. They're light. What are these usually filled with? And, where can people find these in aerospace and, defense market applications?
So they're filled with virtually anything. And just like your CO2 tank or your nitrogen tank that you see in the back of a shop in a manufacturing facility, um, it can hold any type of gas. And we have experience with a myriad of gases, everything from oxygen tanks for military aircraft to xenon, argon, or krypton tanks for electric propulsion for satellites. Right now, we have roughly 100 tanks in space in low Earth orbit and very low Earth orbit that are holding those gases. We also have tanks that are used in launch systems that hold oxygen or hydrogen, nitrogen for fire suppression, and then other more esoteric chemicals or gases that the customers need. We One of the benefits of composite pressure vessels is we can choose the membrane on the inside so that it has the material compatibility to hold whatever gas or fluid um, or whatever the customer needs. Because the strength comes from the carbon fiber, the inside liner is what causes or has the stops the permeation and has the compatibility with whatever fluid or gas customer is using.
Yeah. What's some about these pressure vessels that most people just don't really understand and is misunderstood that if they knew a little better, they'd understand maybe why these are so hard to manufacture and critical that they must be, you know, as best as they can be, lightweight and strong, things like that.
Pretty broad question, but the, there's two things that people don't understand, and one is the sheer quantity of composite pressure vessels or pressure vessels in general that are required in a space system. The original the original space shuttle had dozens of different, and then they were composite pressure vessels manufactured quite differently than we do with ours. But this was the necessity for storing compressed gas in a safe manner goes back to the beginning of the space race. So one thing that people don't understand is how many of these are out there. They're just hidden. No one really thinks about them when you look at the systems, but they are an important or vital component of everything that we do in space. Um, and because of that, they can't be a problem. Um, the first impression that many people have when they hear about composite pressure vessels is, oftentimes in the news, if there is a problem in a launch, so SpaceX had some issues and it was blamed on the COPV because there was an issue with that interface. So when people hear about our product, they only hear about it in the when there's bad news. When things go as planned, we're kind of an often forgotten part of the entire system. But it is critical, it's necessary, and it has to be done in a safe manner. Um, I had no idea getting into this business how much testing we'd have to invest in. I joke sometimes that we're a testing company with a small manufacturing wing rather than the other way around because of the amount of destructive and non-destructive testing that we have to do before we get any product in the hands of a customer, regardless of what the customer is using it for. Because at the end of the day, if the pressure vessel has a problem, we're storing thousands of psi in these of gases that are sometimes flammable and sometimes not. But if something bad were to happen, it could jeopardize a launch. It could jeopardize lives. So doing this in a safe manner is validated through just exhaustive testing um, that that we do each and every day. It's pretty incredible the amount of torture that we have to put on these before they can go on a system. Um, and because of that, that's really what's given Steelhead an interesting position in the ecosystem is that we have had zero infield failures, and because of that, we're one of the go-to suppliers for let's say a satellite that is going on a SpaceX rideshare because we're just the easy button. We make that a very simple choice and low cost compared to trying to start from scratch.
No, today's kind of special because it's actually the 56th anniversary of Apollo 13 getting back to Earth
Mm.
safely. That happened exactly 56 years ago to this day. And that was caused by an explosion in an oxygen tank. I don't know how much insight you have about, what really went wrong there, but maybe you could enlighten us with, you know, what that tank was and how they're different now today.
The We don't do much in the liquid oxygen space. That's a tangential and complicated field, or any of the cryogenic gases are challenges that we don't necessarily deal with. Our products are compressed gases in general, or compressed gas with the intersection of a fluid, more at ambient temperatures. So our product is more on the high pressure, not on the very low temperature side of things. Um, there have been quite a few issues with, well, liquid hydrogen or liquid oxygen tanks, just because dealing with cryogenics is a real challenge. Um, our oxygen tanks, I did mention we make oxygen tanks, but those are mostly for aircraft, and that's like emergency air for aviators, and that's compressed oxygen, not liquid.
You know, Now these tanks you have, they have to be safe and you have to test them. What does that testing look like? Do you just take them out to the shooting range and,
Yeah, we do that.
fire some guns at them? Okay.
That's one of the tests. Um, yeah, we test them. There's over 30 tests that we have to conduct on our products before they're they're validated or certified. The first test we do, and we do this pretty much every day, and that's a burst test where we take a vessel and we pressurize it with water or hydraulic fluid, and we take it to failure. And that failure needs to be some multiple of operating pressure. And that depends on the certification or the customer. But for products that are, let's say, a standard Department of Transportation gas cylinder, that's a 3x safety factor. So if we have a 5,000 psi operating pressure tank, which you can see in the back behind me, that's a 5,000 psi or 350 bar tank. It can't burst at anything less than 15,000 pounds per square inch. or roughly 10,000 or 1,000 bar. So that's the first test, and that's a test we do on every design, and every batch that we manufacture, we have to test one of the lot and make sure that we're still within that. Um, but that's just the scratching the surface is that first. The second test is a cycle test where we pressurize and depressurize it until failure. And one of the cool things about composite pressure vessels is when they fail in a cyclic mode, we get something called leak before burst. So the gas or the fluid will leak out through the carbon fiber without causing an explosion. And that's an inherent safety we have over all metallic vessels, which when they fail, they fail in a catastrophic manner. We have a leakage where we don't have any shrapnel, and there's no risk of explosion upon that happening. We have to prove that. So that's two tests, and then the rest. And I don't want to spend our entire time going through the litany of the other 28 tests, but they're environmental tests, bonfire tests, gunfire tests, drop tests, impact tests, flaw tests, various environmental cycling tests. We have to do tests on the materials, on the liners themselves. Again, there's so many different tests, and they're all to try to mimic what's the worst thing that could happen in real life. What if you're on a satellite and you get hit by some space debris? What's going to happen to the tank? Will it survive? If it does fail, how will it fail, etc.
Yeah. Now, you have some pretty big customers who are getting these from you, and we don't have to go into detail on who they are, but very large companies. What's stopping them from just manufacturing their own?
Well, some companies like SpaceX, they're a customer, but they also have vertically integrated their own composite pressure vessel manufacturing. But they're big enough and they need enough of these to justify it. Honestly, besides them, it doesn't make a whole lot of sense to do what we're doing. Again, the cost of our tanks versus the cost of erecting a manufacturing and testing facility to do these, you have to have a pretty high quantity to justify that. Now, that being said, there are some companies out there who have gotten into this market. I don't know why you'd want to do that. Um, it's a it's a lot easier just to buy from us in general. There's one company, I won't mention their name. They uh, they started manufacturing the tanks, but they had no testing services. So we started doing testing for them and started finding problems in some of their designs during testing, and they ended up just now buying tanks from us rather than trying to do it themselves. There's a lot of art, um, a lot of trial and error that goes into this. Honestly, had I known how difficult this is, I probably would never have started the company. But it's too late now. Um, and there's a reason there's not a whole lot of composite overwrapped pressure vessel manufacturers out there that are doing what we're doing. It's a it's it really is advanced manufacturing at its finest.
Yeah. You sit at the crossroads of a lot of different industries that use your product. Can you talk a little bit about it? I know there's, aerospace, space and defense, but there's more than that. What are some of the other industries you're working in? What are some interesting ones that people might not realize?
That's an interesting question, and it's also been one of our problems. And how do you explain what we do when we're doing something for so many industries? Everything from buoyancy control for underwater autonomous vehicles, we've got a product that is used in scuba diving for a lightweight safety scuba diving product. Ironically, that scuba tank was a satellite tank, so it's in space and it's being dove. We've got about 2,000 different dive tanks in operation right now. So there's dozens in space and thousands underwater of the identical tank, same exact tank, same certification, same standard, same safety factors. But I guess we could say we have more scuba tanks in space than anybody else. But it's that interesting. How do you have a product that serves, the needs of anybody that needs to safely store a gas in a lightweight, validated application? We've done we put a diaphragm or a bladder in our tanks. That was our original product. It's been used on some of the more advanced stabilization for advanced robots that walk and jump and run. And that same type of, dampening or suspension then worked with us or helped us as we got into production on two very, very high-end car platforms where they wanted to lightweight their suspension, active suspension, and they went with us. So we did what's called a PPAP, which is an automotive production part approval process. So meaning that we were able to make large quantities identically and be audited by that. So when one of our satellite customers came to us saying that they needed to have thousands of tanks for their constellation, we did what I believe is the first PPAP, which is, again, automotive production approval process for tanks that are in space. These are all the same process, same type of validation, manufactured in the same facility, but being used in pretty much every industry that you can think of. Oh, we just got a customer that has a maritime racing organization just built us into their system, and that's for weight, but it's also for corrosion resistance. So it is the intersection of a lot of things, but it really is the aerospace, space, and defense that we're leaning forward on because we see a need in the market, and customers that are clamoring for product that really on the space side. One thing to note is because of the risk of space junk, the FCC has mandated that passive decay of satellites is no longer permissible. They have to actively reorbit at the end of life, meaning that satellite companies now have to think about adding propulsion. And if you add propulsion, we are the easiest solution out there, I think. We're very inexpensive for what you get, and we can give a validated, safe solution for a satellite that needs to re-enter or demise upon re-entry, which we can talk about if you're interested in that topic.
Yeah, absolutely. So one of the first things I was thinking is, you have these scuba products and you have these products in space. You have, a lot of atmospheric pressures being deep underwater, and then you have space, which is no atmospheric pressure. Are these the same tanks that are able to withstand both of that? Is there a type of limit you have to be concerned it with that, it can't go up too fast or else the pressure will become too immense, or it can't go down too fast? I'm trying to get a sense of how you deal with all these different altitudes and atmospheric pressures with these tanks.
It's all through testing. It's all through additional destructive testing. But they're identical tanks that are in space and being dove right now. So as we speak, in low Earth orbit and very low Earth orbit, and in the water somewhere in the world is a steelhead tank which is identical. Um, One of the questions that we get frequently, or more frequently, is about that submarine side because of the catastrophe that we saw on the composite submarine, and if that's what we have to deal with. The answer is generally no, because, well, first of all, we don't go that deep. But second, we have pressure on the inside of our tanks. So that is excess of what is on the outside. So as long as we're holding pressure that is more than the force of the water, we don't have any issue of collapse. And even if we do have more pressure on the outside, our tanks are very, very robust. I wouldn't put people in them and use it as a submarine because of that. This is just not what we're doing. But we do have product that is very, very deep in the ocean and has been there for a long time safely.
Yeah. Let's talk about end-of-life satellites. So just the idea there's a satellite, its time is ending, and it needs to be taken care of. Walk us through what that process is and where your tanks are involved in all those steps.
So one other thing that people, hear about COPVs or composite pressure vessels, occasionally you get a something that ends up in somebody's yard, which looks like a black ball of singed something that will be shared on the internet of what is this? And that's what happens when a composite pressure vessel uh, has an issue and explodes or re-enters orbit. Because the carbon fiber itself won't melt, or the word that the industry uses is demisability. So for one of our bigger customers, and we're seeing an increase in this now because of the need to actively re-enter or burn up the satellite at the end of life, have some propulsion on board, and not have something ending up in somebody's yard in Oregon and causing a news or headache, or even a risk property damage or life. We've we have a class of products. I don't know if you can see me very well. I'm in my conference room right now. There's a kind of yellowish tank behind me.
Yep.
That is a certified fully demisable tank. Again, meaning that it completely burns up upon reentry, so that there would be no residual that would then um, uh, cause any potential of life or property damage. And that is done through choosing different materials. They're a little heavier, or quite a bit heavier. They can't have certain materials in them, but they are for that purpose. How do you have something that will not cause space junk and will burn up upon reentry and fully demise? And that tank is an actual satellite tank. Oh, and you had mentioned gunfire. That one has a bullet hole in it. So if anybody's ever in Colorado and wants a tour, I'll show you around, and I'll show you the bullet hole in that tank. Instead of carbon fiber as the reinforcement, again, the carbon fiber doesn't burn up. We use an aramid, or like a Kevlar, which is an organic material for reinforcing, rather than carbon fiber, which is carbon. And that's so that it burns up upon reentry at these temperatures. And
Yeah.
we've got a few of those in space right now, and just got an order for about 20 more that we'll deliver by the end of the year for the fully demisable satellite tank. Yeah, those
Yeah.
are those ones are xenon tanks in particular. We do have a higher pressure one that was designed for krypton.
There's a lot of these tanks, and I'm sure they vary in all sorts of size. Like, how small do they get? Can they get to the size where they can fit in your pocket, or how big can they really get? I guess the answer I'm looking for is the sizes that you create.
Sizes that we create, because if you look at some of the launch tanks that are being made by the launch companies that are for the liquid oxygen or liquid hydrogen, they're the size of my this conference room. Or bigger.
Wow.
They're huge. That's not our bread and butter. And those ones are also they're manufactured differently. For us, the smallest tank that we make, it's the size. This is a 2 liter tank, so 2 water liters. And the largest one, it's behind me. It's a 550-liter tank. The problem that we're trying to address, and I would love to be on a soapbox a little bit for our customers, of every customer seems to want a different size and a different pressure, because the design engineers leave the pressure vessel to the very end, and then they maximize their real estate, and then they can't find what they need. So we have done quite a bit of effort of having different sizes, different pressures, but every day I get a customer that wants a size and pressure that we don't have, because they're trying to solve their own issues, and we can do it. The issue is on certifying it and validating it. That if you want a custom tank, it's going to cost you I'd mentioned roughly 30 destructive tests. We'd have to design it, we'd have to engineer it, we'd have to manufacture, then do our iterative testing, and then have witness testing of 20 to 30 destructive tests, and then submit the paperwork to the governing bodies. And that could take 12 months, and that could cost an extra $100,000. So to the extent that we've already designed it and we're already making it, it's just a lot easier. Yeah, so we're between 2 and 550 liters. Our main product lines, though, are between 20 liters and 270 liters. And 3,000 psi and 5,000 psi, I guess, are the two main flavors that we sell the most of.
Yeah. You're talking about just how difficult these are to manufacture, and you have all these different sizes and made with different components. So we can get an idea in our mind, like how does how are these manufactured? What does it look like? What's the process? And can you have like how much can you automate from a machine to just build this uh, with all these different SKUs and variations?
So if we talk about most of what we do has a metal liner. For space, we generally do metallic line, called Type 3. So we take a seamless extrusion of aluminum. Seamless meaning there's no welds and there's no seam on the side. So it's an extruded tube. And then we have a machine that's an open mandrel spin former. Really pretty cool to see. It's a fully CNC operation where that tube is then spun at high speeds and heated up with torches. And then, like a potter's wheel, the metal is pushed down. It's not extractive, it's not additive. It's pushed to create domes. And the domes are the tapered ends of the tank that we then use for sealing. The cool thing about it is that without any welds, without any seams, it becomes virtually impermeable to whatever gases you're using, because it's got a solid homogeneous aluminum liner, we call it. We don't have to deal with the issues of welds, which is additional inspections, and welds are generally the failure point. So the first step of doing this is how do you create that inside liner, that the material that you have that holds the gas, keeps it from escaping, and then turns into the the inside of the bottle. Um, and that's a very interesting, rather quick um, part of the process, where let's say it takes 4 minutes per dome to create it. Then the step after that is we machine the port ends, we add any features that we need to the liner, and then we do the carbon fiber reinforcement, and this is done through another CNC. So it's all computer controlled process called filament winding. The difficulty of the filament winding is we want to have the right failure mode, the right amount of strength, but have as little material on as possible because it is the most expensive component that we have in our manufacturing. But those are the two processes they're very highly automated. We've got a large database of programs, um, and for changing sizes, as long as the size is only being changed in length, it's almost trivial to change it because the spin forming, we just cut a larger tube and put the larger tube in our spin forming, and then we add length to it in the winding. And from a validation standpoint, it's a rather inexpensive way for us to qualify a vessel is just by adding length or removing length to have a different size, as long as we got the same pressure on it.
Got it. So how many different versions of these tanks do you have, would you say?
Too many. The
Is it the hundreds? Is it dozens? Is it
it, it,
thousands?
it would be dozens. So we have about 20,000 tanks that we've sold in the market, and there's probably 50 different SKUs that we've done for that. And again, some of those were custom for custom designs with the rather low quantities. Um, the flight hardware for some of the launch companies, we've sold, let's say, 15 of a very custom, very unique tank to one customer. And then we have some products like I'd mentioned the satellite tank that we use in scuba, use in other applications. We've done, it seems to be a good volume. They're 8, 10, and 12 liters, and we've sold thousands of those for just various applications. It's as close as we have to a catalog product.
Yeah. One thing I'm thinking of is just, how strong these really are. If I had, a tank that was at completely full, like fresh and ready to go, at what height would I drop it to where I would see an explosion, and would that change depending on what was inside it?
Um, so if you were to so we have to drop test these. And then after we drop test them, we have to cycle them. In terms of how high, I don't know if you could get a tank to burst upon dropping it at any height.
Really? Well,
Uh, maybe, maybe these are very robust. Um, the uh, the only way we really get them to burst is by taking them to very quickly to a multiple of their operating pressure. But we have to, I mean, we test these in ways so that if one were to, you again, we got products in um, that are oxygen tanks for uh, military aviators, and those have to withstand an airplane crash. So it's,
Yeah. Okay. Yeah, growing up, I'm a little familiar with these tanks. I used to play paintball, and with
yeah,
paintball guns, you have these small compression tanks. And, there's always just this is a tank with a lot of pressure and makes you a little nervous around it of just, how much can this endure before it breaks? So the answer to that is, from a drop test, most of these, they're just not gonna break.
but it's a good point, and people underestimate how dangerous these high pressure tanks can be. And even though we uh, we try to make them in a way that they're not indestructible, but very safe. There should be a handle with care. So I mentioned we're doing some products in scuba, and traditional aluminum or steel tanks, they get abused like crazy, and people don't fully appreciate how dangerous 3,000 psi or more of compressed gas can be. It, it's it's honestly frightening. I think that people would throw them around less and treat them a little nicer if they realized how dangerous, it, if something bad were to happen, it would be. Um, for us to get to do this, to get our products in the market, uh, there are standards, there are ISO standards, there are also regulatory bodies out there that dictate these tests. So it's not us coming up with a test and saying, okay, this is how we should test it. It's a it's a standard body. Um, an example of the oxygen tanks I had mentioned, they have the traditional tests that we would have across our portfolio, but they add other tests, like rather than shooting it with a bullet that just to penetrate the tank, they shoot it with a 50 cal incendiary round to ensure the metal doesn't catch on fire when the oxygen is under pressure, because all metals burn in high pressure, high oxygen environments. So we have to choose metals that don't burn and have to validate that through a very special test, because they don't want someone shooting a round and causing a loss of a pilot's life if that tank got hit.
About how many life cycles are these tanks good for? Like, just keep filling them up? Do they change over time and need to be replaced?
They do. So in general, composite pressure vessels have a life of the goal is 15 years in general. We have products that have longer lives than that and shorter lives than that, but a 15-year life would represent, let's say, 15,000 cycles or 10,000 cycles. It depends on the use case, but it's thousands of cycles. We did a project for mobile machinery where they needed us to have a 2.5 million cycles, and we got there. So did have a product that had, I think, I cycled 2.5 million times. Um, we had to over-engineer that one a little bit.
Yeah, how do you test for that?
You cycle it.
You did 2 million cycles?
We did 2 million cycles.
Wow.
And they're not gas cycles. If it was gas cycles,
Okay.
it would take a lifetime to do that. But they're so it's hydrostatic. So we've got a enclosure just in case anything bad were to happen. And then we've got a pump that pressurizes and depressurizes 5 times a minute, and just let it run day in and day out. And again, at the end of life, these leak before they burst. So, or they're designed to. And so that as long as everything's going right, you get a leaking of the fluid so that it just no longer holds pressure. And that's how we determine when the end of the life was of that. So that's what we call, a cycle test.
Got it. And I'm thinking about, multiple cycles and filling these tanks. And the question is, how do these get filled? And what I mean by that is there just another tank that's bigger that has the gas or liquid that they need? And if so, who fills that tank? And do these tanks just keep getting bigger and bigger? At what point is there no tanks filling other tanks?
Well, sometimes it's another tank where it's a higher pressure tank that we use to fill up our tanks. Um, Lots of times you've got a compressor behind it, so you've got a gas compressor that then. So when you think about like a scuba tank, the scuba tanks are filled at the dive shop with a compressor that just takes ambient air and then pressurizes it to 3,000 psi or more to fill up the tanks. Um, some of the more difficult gases, you would fill it from a bigger tank into a smaller tank, and that would be done by you'd buy the gases from one of the industrial gas companies.
And
But
do they have that in an even bigger tank?
some of it's in even a bigger tank. They deliver it. It all depends on what your needs are, and if you have the gas available, and if you have a compressor available. Um, but that's there's not one answer for it because again, we don't deal with just one gas. Uh, Nitrogen, and we do a lot of nitrogen, and those are done from larger tanks from that are pretty readily available, or
No.
or nitrogen. We do generation of a nitrogen in house, and we'll compress that. Pretty easy to do.
So when I think about these tanks being used in space, the application of it helps with propulsion and oxygen if needed, and with, a commercial airplane, there could be a lot of use cases for these tanks. But what about something that doesn't have people and it just needs to move fast, like a hypersonic? Where do these tanks come into play with those?
So one of the business lines that we've been doing for quite a while, but now we're seeing a tremendous demand for because of some recent geopolitical uh, issues regarding U.S. Supply chain of interceptors, et cetera, is uh, something called rocket motor casings. And there's a class of rocket motor casings that are made out of composites, and that's for lightweight. It also um, gives you the ability to have your, whether solid or chemical fuel, more of it because you need thinner walls inside of it. And these are basically composite pressure vessels with different criteria. They have to hold high pressures, thousands of psi, but deal with very high temperatures. And of course, they're single use. But it looks like one of our tanks with a few extra bells and whistles that are manufactured in ways that we're very comfortable with. But we're seeing a big amount of demand from the prime defense contractors for composite rocket motor casings, and we're fortunate that we have a history and a heritage of manufacturing some of those, so that I think we can really be a quick solution, doing these in a safe and very automated way, and get help the U.S. defense complex have things to keep people safe, to shoot down threats, and we're very active in that. and we're very active in space defense as well. Um, two markets that a year ago I would have said were not all that interesting, but should represent 80% plus of our revenue next year.
Oh, wow. Yeah, I was thinking about it, and the timing in the market, it seems quite optimal for you guys. I think, several years ago when there was warfare started and we weren't seeing, a Pacific war, we were seeing a war in Ukraine or the Middle East. We have these drones, and these drones, they use these brushless DC motors to power the quadcopter, and those became such a high demand item, and companies who were building those, they couldn't fulfill the amount of demand they were getting. But
Mhm.
now, as we shift to seeing things like Golden Dome, space defense, and political tensions where a possible Pacific War could happen, we have to start stockpiling on hypersonics, and a war that's across the Pacific Ocean, thousands of miles. These quadcopter drones, they're not really gonna matter as much. What's gonna matter is these very fast flying interceptors and missiles.
Yeah.
So as the market changes, you said you're seeing how 80% of your demand comes strictly from that. How are you going to be able to scale up against that? And have you really seen, the total market size, or has that not even presented itself yet just because the demand really hasn't stopped?
Well, to scale, we already have the basic infrastructure for scaling to most of what we need. Everything that there's no additional, let's say, new type of capex that we would need. We'd have to just add staff and add equipment, and of course, we'd need to raise money in order to do that. Um, in terms of the market size, in March, we responded to 19 RFPs um, from names that you have heard of and names that Balerion is involved with as well. The total size of the quotation across all of those, it's a little bit nebulous, but it was $319 million of rocket motor casings and composite pressure vessels for space demanded in 2027. Of course, we can't fulfill all of that. We're not trying to, but I think we can be a pretty meaningful part of it. There's not a whole lot of companies in the US that do what we do. Actually, very few, and no one that can do it as inexpensively as we can, because we have cut our teeth on doing high volumes for alternative markets. So the legacy suppliers are really great at making exquisite components. The word that you hear from the military now is attritable, which means it's low enough cost that it doesn't matter if you lose it. So we come in, try to make things at a competitive price using highly automated processes, so that we can meet the needs of thousands or tens of thousands of tanks at a reasonable price with all the safety that we need. Um, and that's why I think we're in a pretty good place to benefit from this increase in demand for interceptors, for hypersonics, and for various in-space satellite constellation products that need to have thousands or need to have tens of thousands of products. But it's kind of interesting or kind of spooky that a 30-person company in Colorado can be at the intersection of the U.S. defense priorities and have that kind of come out of nowhere.
No, those people are coming to you with these orders, what's the manufacturer lead time on your products, or what's the standard manufacturer lead time to get these composite solution, these tanks?
It varies. Many of these companies have pretty aggressive timelines, but because we have all of our design, all the manufacturing, and all the testing internally, we've got pretty quick lead times to at least get prototypes or first articles out in the market. If it's a product that we've manufactured before, our lead times are in weeks. For some of these custom, say rocket motor casings, some of our customers need products by end of summer, and we can meet those timelines.
Okay.
It also differentiates us from some of the legacy manufacturers of these tanks that have been in space for decades, is that they're comfortable with 24-month lead times. That's just not acceptable to our customers right now with the urgency of the demand from their end customer.
Got it. And can these tanks be used for alternative use cases, say energetics? Basically, what I'm saying is, can these tanks, because they have, so much pressure in them of certain gases and liquids, could someone come along and say, I would like to put this into an energetics weapon, a bomb?
We we have not seen that. We do everything we can to make sure that they're not bombs. Um, but there are some use cases where these become very interesting um, propellant solutions where you have a combination of a fluid and a gas to move vehicles at hypersonic speeds, where you could then have a energetic being introduced at a very rapid pace. But the tanks themselves, we have not seen anybody that wants to use those in a bomb-like fashion. It really is, how do you take something that take advantage of the lightweight, the high strength, and the material compatibility, and use it to deliver something. And that's why it's so applicable for things like interceptors.
Yeah. And if you needed to fulfill, all this demand, and you needed to fulfill it fast, and you had the capital, you had, you know, unlimited money to work with, how would you scale up the production? What are the main choke points that exist today? Is it supply chain? Is it, um, you know, talent? What would need to change?
It's a great question. Right now, we have the ability to have about 10,000 tanks manufactured a year on a single shift in our facilities. For us to go beyond that, we'd have to find where the holes are in our manufacturing and where the bottlenecks are. Um, Filament winding, where we reinforce the structure with carbon fiber, that becomes a bottleneck pretty quickly. And we'd have to add capacity in the filament winding side. Um, Testing can be a bottleneck as well. You had asked about cycle testing before. Those cycle tests, it can take quite a bit of time for us to test on that machinery. We added a second cycle tester this year, and we may have to add more so we can have parallel products being developed. But in terms of meeting the demand, the supply chain, I think we've got a pretty mature supply chain in place. Because we're vertically integrated, we can not be at the mercy of outside suppliers when it comes to most of our processes. So I think we're in a good spot. We would just need the demand, and we need the capital. Well, we have the demand. We need the capital, and then we need to, um, you know, go forward and do it.
Uh,
You have to be a firm demand.
I think you'll have some
Uh,
solid demand
we've
in the
made the
future.
mistake before of thinking that we had demand and scaling up before it, and then it has kind of uh, fizzled or gone a different direction. Hoping that this time is different, and the real hope is that we can find the capital and the strategic partners that can help us move this to the next level.
You know, well, Andrew, from our conversation today, if there's someone listening and you wanted them to, finish this conversation and just have one big takeaway from everything we've talked about, what would you want that to be?
I think the big takeaway is that well, first of all, it is scary how dilapidated our military industrial base is, and that we are companies like Steelhead that have kept U.S. manufacturing and kept a U.S. supply chain are well positioned to solve problems of the next war or the next confrontation as opposed to the last one. And I'd love to continue the conversations. We're located in Golden. It's a pretty cool tour. Would love to show anybody who wants to see how these are manufactured, show you how they're made and how we do it. And if anybody out there is looking to be part of this as well, we're looking for the capital. We're looking for the support, the help. But we are. I think we're going to have a pretty fantastic next 18 months, and happy to be part of it.
Very good. Well, Andrew, thank you so much for taking the time to chat with us today. This has been a great conversation, and I look forward to seeing what Steelhead does in the future and staying in touch and talking again soon.
Really appreciate it. Thanks, Aidan, and
Eh,
thanks, Barbara, and really appreciate it. And yeah, let's be in touch.
Thanks. Thank you,
Thanks.
everyone. Take care.